Okay, well, welcome back. It's 2 o'clock in Michigan, so we'll start the 1 o'clock talk. Our next speaker is Misha Tyomkin from Dartmouth College, who will speak on numbers associated with a strong Morse function.
Yeah, thank you for the introduction. So let me start by thanking the organizers for the opportunity to speak here. It's my pleasure. So I'm going to report on a joint work with Petya Pushkar. It's now posted on the archive for some time on numbers associated with a strong Morse function. So the plan for the next 20 minutes is the following. So I'm going to be basically speaking about a certain invariant associated with a strong Morse function. So first, I'm going to give you the setup. So I'm going to say what I'll be constructing, and then I will give you the actual construction of this invariant. So how can you construct the output given the input? Then I'm going to present the basic facts about this invariant. And I will end by a theorem which comes in a bundle with two versions, baby version and the grown-up version. All right. So the setup is the following. So let M be a closed manifold, smooth, and F be a strong Morse function. So what I mean by strong here, I mean that all the critical points have different critical values, right? So the situation on the situation on the right is prohibited, right? So it is still a generic condition which prohibits two critical points to be on the same level, and let big F be a field in the algebraic sense, so a ring with a division. So the input of the invariant is F and big F, so a function and a field, and the output is the following thing. So it consists of two parts. So the first part is the pairing of some critical points of function with neighboring indices. And by pairing here, I mean the decomposition into the disjoint union of pairs. So each point can be either non-paired at all, or it can belong to a single pair. And second, the Bruhat number on each pair. And by Bruhat number, we mean the number lambda, which is a non-zero element of the field, defined up to psi. So these two things combined are called enhanced barcode. So the example is given on the right. So by dots, I mean the critical points of the function. This black numbers represent the indices of the critical points. The pairs are depicted by bars, so hence the name barcode. And the Bruhat numbers are drawn in blue. So the field is AQ, and so have 3 pairs and 7 points. So one of the points is unpaired, and the indices are given in blacks. So for example, this long pair connects two critical points of indices 2 and 1. So each critical point is therefore either upper in a pair or lower in a pair, or if it is not paired, it's called homological for the reasons I will be talking about later. So there are 2 warnings here. So the first warning is that I don't fix any Riemannian metric on the manifold, and hence there is no Morse complex of the Morse function f. So I take as an input only the function and the field, and that's it. So second, paired points need not be neighboring in the sense of the natural linear order on the critical points. Yes, so I can go from bottom to top. For example, this long pair connects 2 points which are not neighboring in the sense of this linear order, because there are 3 points in between. Good. So now I want to pass to the construction of this invariant. So how do I construct this enhanced barcode given a function and a field? All right, so what do I have to do basically? Given 2 critical points of the function f, x and y, I have to tell you whether they're connected by a bar, so whether they're paired or not, and if they are, what is the number on this pair, right? Okay, so let me do this. So the notations, let me say that the index of x minus 1 equals to the index of y equals to k. So they are in need of neighboring indices. And also assume that f of x is greater than f of y. So x is higher than y. This is the only condition under which the two can be paired. So there is the classical notion in the Morse theory, which is called the sublevel set, given here. So if A is any real number, then I can consider MA, which is the sublevel set of the level A, defined as all the points P in the manifold M, such that the value of this function f on P is at most A, right? Classical thing. So what do I have now? So the picture is given on the right. So don't look at the definition yet, just look at the picture, right? So I have x, which is higher than y, f of x is greater than y, right? And index of x is one greater than that of y. So, and then I can consider this topological pair, yes? So definitely, since f of y is less than f of x, this sublevel set is the subset of the sublevel set. So I can consider the following topological pair, and then I may look at its homology over the relative homology of these two spaces in dimension k over f, right? So this is a vector field, a vector space over f, right? So in this vector space, I want to consider two homology classes, drawn in purple and in blue. So big X. So let big X be by definition the attaching sphere for X. Yeah. So on the picture k equals to 1, so index of x is 2. So it corresponds to a 2 cell which is attached along a circle. So this circle is a cycle of dimension 1, and it's called the big X, and the big Y is the attaching disk for Y. So here in the picture, Y has index 1, so it corresponds to a segment, and I take the class of the segment, the fundamental class of the segment. So this gives me two elements of this vector space, two vectors, homology classes, and then the definition is that x and y are paired with Bruhat number lambda if x equals to lambda y and both are non-zero. So if these two classes are proportional in this homology vector space, then I say that the two critical points are paired, and the coefficient of proportionality is defined to be the Bruhat number, right? So that's the definition. So let me note that first, I didn't fix any orientations of my classes. So therefore, this lambda is only defined up to sign. Now that's okay. And second, given such a definition, one has to check something, yes? So I claimed here, yeah, that the pairing is the decomposition into disjoint union of pairs, right? So it doesn't follow immediately from this definition that each point is being paired with at most one other critical point. But that's true. So you can check this by writing some exact sequence of a pair, or maybe of a triple or so. Yeah. So this is the construction. Right. So the references is that without the Bruhat numbers, it was constructed by Barannikov in '94. And yes, so the terminology here is that if you don't care about Bruhat numbers, then this called just the barcode. And since there is a number attached to each pair, we call it enhanced barcode. So the barcode proper was constructed by Barannikov, and now there's a popular tool in applied and symplectic topology. It's called the persistent homology. And some similar ideas of Bruhat numbers over Q, over the field Q, appeared independently in the work of Lepetruc, Neer, and Viterbo. Good. So what about basic facts about it? So first, the example. So let M be the RPN. Big F equals to Q. So let me take the standard Morse function on the RPN So by standard, I mean that it gives me the standard cell decomposition, and it has a critical point in each index from 0 to n. So there are n plus 1 critical points, and the enhanced barcode of the standard Morse function on RPN with field being equal to q is given on the right. So almost all points are paired, and the number on each pair is plus minus 2. So the only point which is not paired is the bottom one, and maybe the top one, depending on the parity of n. So if n equals to 6, then well, at the bottom, the top critical point is not paired. If n equals to 7, say, then it is paired. All right. So the next property is that the dimensional homology of M over F equals to the number of homological critical points of index K. So this explains the name. So the number of unpaired critical points is just the dimension of the homology in the corresponding degree. And so the next fact is that given any manifold M of dimension big enough and any lambda in any field which is Q or P, one can find a Morse function F on M which has a pair with Bruhat number plus minus lambda. So informally, this means that the individual Bruhat number can be any given in advance. You give me the manifold, you give me the number, you give me the field, and I give you the function. So there's no control over the individual Bruhat number, and as a consequence, I want to know that the Bruhat number over Q may well be non-integer. So basically any rational number defined after sign. All right. So let me now then move to the baby version of the theorem. So as said, a single Bruhat number can be any, but let me now define the following single number as associated to the function. It's called the tau of f and bkf, and that is defined by this formula. So here theta is a pair, lambda theta is a Bruhat number on a pair theta, and the degree of the pair is defined by this formula. So it is the index of the upper critical point. So I take the product of all the Bruhat numbers, but some of the Bruhat numbers have to be raised to the power minus 1 depending on some priority. And that's why we call it alternating product of all the Bruhat numbers. Yes. So by alternating, we mean that it is you have to raise it to the power minus 1 depending on some priority, and this is named in an analogy with the polar characteristic, which is the alternating sum. And in general, the torsion is the multiplicative analog of the polar characteristic. So in all characteristic, you take the sum of all the generators with plus or minus depending on the parity, and here you take the product of all the numbers raised to the power minus 1. Yeah, so now the baby version of the theorem states that suppose that the homology of M vanishes in all the degrees except for the bottom one and for the top one. So essentially, it's more or less the same as saying that M is F homology sphere. Then this tau of F and F is independent of the function. Yes, so individual Bruhat number does depend on the function. The number of all the Bruhat numbers depends on the function, but the product of all of them in the alternative sense is independent of the function. So it depends only on the manifold, right? So that's the first theorem. And so the note here is that this number tau of F and F can be expressed in terms of homology of M over Z. So as an invariant of the manifold, it is not very interesting. It just expresses in terms of the integral homology. But the point of this baby version of the theorem that this number is independent of the function. Right. So the example is again take M to be RPN, F to be Q. Then now if you take any Morse function on RPN, any some Morse function of RPN, then the alternating product of its Bruhat numbers will be equal to the 2 to the power n divided by 2, and where the brackets denote the integral part. So for example, if n is 6, then it is 2 to the power 3, which is 8. Okay, so that was the baby version. So now I want to move on to the grown-up version. So for this, I have to introduce a bit of terminology from the algebraic topology. So pi1 is the fundamental group of M. So let rho be the one-dimensional representation of the pi1. So it's basically the map from pi1 to the GL1 of F, which is just the F star. So you're essentially given the map of the homomorphism of groups from pi1 to F star for some F. And this is called, in the fancy words, one-dimensional local system on the manifold. So given such a one-dimensional local system, one can consider twisted homology of M with coefficients in rho. Yeah, so this is called twist homology, or the homology with coefficients in local system. So this is still a vector space over F. Okay, so now given the Morse function F and rho, the representation of pi1, we can construct in essentially a similar way. So I'm not giving the precise definition, but it is essentially the same. One can construct the twisted enhanced barcode, and hence we have the twisted Bruhat numbers. Yes. So this depends not only like on the field, but also on this representation of the pi1. So the point here is that the critical points are the same. Yes. So they are still so what I'm pairing is still the critical points of the function F, but now the pairing may be different and the numbers may be different because I take this representation into account. And the only like difference is that now lambda is defined not only up to sign, but also up to multiplication of by the image of pi. Yes. So rho of pi is some subgroup of F star, and there's this greater ambiguity in defining the Bruhat numbers. So now the product of all of them is defined in a similar way. I just take the alternating product for the Bruhat numbers. So then what's next? So suppose that twist homology vanishes. So this is surely a very strong condition, but still, if it is satisfied, then one can define the Reidemeister torsion of the manifold, and it lives precisely in the same group, in the same quotient group. Tau R is the Reidemeister torsion. So it is a topological invariant, a classical one, and it can be used to classify the line spaces. So the point of this invariant is that it is the first, maybe non-trivial invariant, which is not stable under homotopy equivalences. So, for example, the homotopy groups and the homology groups are unable to distinguish homotopy equivalent spaces, but Reidemeister torsion is able to distinguish homomorphic but non-homomorphic but homotopy equivalent spaces sometimes. And the famous example is the line spaces. So you can use the Reidemeister torsion to classify the line spaces. So Reidemeister torsion itself, it doesn't have anything to do with the Morse theory. It's just the topology. It's just the invariant from algebraic topology. So the grown-up version of the theorem says that suppose I'm given the one-dimensional representation of the pi1, and suppose that twist homology vanishes. So I am in the position of defining the Reidemeister torsion. Yes. So the Reidemeister torsion is only defined when the twist homology vanishes. Then Reidemeister torsion equals to the tau of F and rho. So in words, so in particular, this tau is independent of the function, and in words, the alternating product of all the twisted Bruhat numbers equals to the Reidemeister torsion. Yes, in particular, it is independent of the function because the Reidemeister torsion depends only on the manifold, right? So this is the grown-up version. Maybe in the last minute, I want to quickly run through example, which is the line space, the three-dimensional line space that is given by three numbers P, Q1, Q2. So the fundamental group is ZP, and there's a Morse function which gives you the standard cell decomposition of the line space, which has 4 critical points of indices 0, 1, 2, and 3, and the line space here is three-dimensional. So if I just so I take F to be C, I take the representation which maps the unit in ZP to the primitive root of unity, and the two barcodes are given on the left. So if you don't twist the coefficients, if you just consider the coefficients in C, then the barcode is this, the left one. So as you see, it does not able to classify the line spaces because it depends just on P. While if you twist coefficients by the one-dimensional representation role, then the barcode looks like this. So the pairing is different, and the numbers are also different. And if you take the product of those numbers, yes, of these two numbers, so you have these two Bruhat numbers, you take the product of them, and you get the reciprocal of the Reidemeister torsion as an element of this quotient set. So this is an example, and I guess I'll stop here. Thank you very much for listening.
Thank you. Are there questions for the speaker?
Yeah, I'd have a question. It may be quite naive.
Sure.
Yeah, but what is the Reidemeister torsion? How do you define it in few words?
So in a few words, you do the following things. So you have the position of the pi one, right? This row. So this it extends to the map from the fundamental group of pi one to the from the group ring of pi one to F. Yeah. So just by linearity, so this is the group ring. So then you have your space X. You consider its universal covering X tilde. So then you have some CW decomposition on X, CW decomposition. It gives you, well, the chain complex, say C of X. It is the complex of three Z modules. So then you might want to lift all the critical points, all the cells up to the universal cover and get the corresponding complex of X tilde, but this is now not a complex of Z modules, but this is a complex of the Z of pi modules. So this is the complex over well, maybe of Z of pi modules, as opposed to this, which is the complex of just free, well, everything is free Z modules. And then you might want to take this complex of Z of pi modules and transfer it over rho by F. So by this I mean that any element of this complex is the Z of pi module, but F itself is also the Z of pi module, right? Because if you have the map from something to F, then this turns F to be into a module over the source. So if you treat F as a Z of pi module, then might the transfer product of two Z of pi modules, the F and the cell complex, and then since F is also a module over itself, then this turns out to be the complex of the vector spaces. This is the complex of vector spaces over F. And then you take the homology of this complex. This gives you the twisted homology. But if the twisted homology vanishes, then you, in some sense, you can define the determinant of this map. So if you have just any base complex over the field, then you might define its torsion by certain determinant which maps the Dirac sum of all the odd chains into the Dirac sum of all the even chains. Even Ci. So if there's no homology, if the homology of C vanishes, then you might then you may construct this isomorphism. Then you take the determinant of this isomorphism, and this is the Reidemeister torsion. Very roughly. I don't know if it helps.
Okay, thanks.
Sure.
Are there other questions? Again, if you want to ask a question, just unmute yourself and go ahead and ask.
I wanted to ask just a quick one. I think this was implicit in your talk, but I just wanted to check that if I ignore the Bruhat symbols, these barcodes, this is what someone who works in persistent homology would think of as the barcode.
This is the same as just the usual barcode. I mean, the definition which is used in persistent homology world is a bit different, but it's equivalent. And also in applied topology, in symplectic topology, if you have the Hamiltonian, then you sometimes also want to consider this.
Thank you.
The barcode, yeah.
Is there anyone else? Okay, well, let's thank the speaker any way we can.